China just built a battery the size of a coin that never needs charging, not for 50 years. You heard that right, 50 years. To put that in perspective, a standard AA battery dies in roughly a few weeks of continuous use. This thing outlasts entire human careers. It doesn't need a plug. It doesn't need sunlight. It runs on something far more powerful and far more misunderstood. This is the BV100, and what's happening inside it right now is rewriting everything you thought you knew about energy. What just happened in China? Imagine holding something smaller than a coin in the palm of your hand and being told it will still be generating electricity when you're retired, when your kids are grown, when half the technology you use today is already obsolete. That's not a metaphor. That's exactly what Betavolt Technology just handed the world. In 2023, this Beijing-based company announced a working prototype of the BV100, a nuclear micro-battery, roughly 15 millimeters by 15 millimeters, thin enough to slip under your fingernail, powerful enough to run continuously for 50 years without a single charge. You heard that right. 50 years of uninterrupted power from something that fits inside a shirt pocket. But here's what made the world stop scrolling. This wasn't a theoretical paper. It wasn't a university concept buried in a research journal. It was a functioning device tested, documented, and moving toward commercial production. Engineers and energy scientists who had spent decades working on battery technology suddenly had one question they couldn't stop asking. How is that even possible? The answer sits at the intersection of nuclear physics and semiconductor engineering, two fields that had never quite merged like this before. And once you understand what's actually happening inside the BV100, you'll realize this isn't just a better battery, it's an entirely different category of energy. And this was only the beginning of what Betavolt had quietly been building. Meet Betavolt Technology. Most world-changing companies don't announce themselves loudly. Betavolt didn't hold a flashy press conference or drop a viral launch video. They published their results, filed their patents, and let the technology speak. Founded in Beijing, Betavolt sits inside China's rapidly expanding deep tech ecosystem, a network of state-supported and privately funded labs pushing hard into the frontiers of energy, materials science, and semiconductors. But Betavolt wasn't chasing the next incremental improvement in lithium-ion. They were working on something that most engineers considered too difficult, too expensive, or too dangerous to pursue at a commercial scale. Their target was nuclear energy, not the massive reactor kind, not the kind that powers cities or submarines. They wanted to miniaturize it. To shrink a nuclear energy source down to something a surgeon could implant, a soldier could carry, or a satellite could run on for decades without intervention. The idea wasn't new. Nuclear batteries, technically called Betavoltaic cells, had existed in research settings since the 1950s. They had even been used in early pacemakers. But the efficiency was terrible, the materials were unstable, and nobody had cracked the problem of making them last long enough, safe enough, and small enough to matter at scale. But Betavolt cracked it, or at least got closer than anyone ever had. The tension wasn't just technical, it was strategic. China had watched the global energy storage race accelerate for 2 decades, lithium-ion batteries dominating everything from smartphones to electric vehicles. But lithium has limits. It degrades. It catches fire. It depends on charging infrastructure. And in the race for technological independence, China needed an edge that wasn't just incremental. The BV100 was that edge. The moment Betavolt's announcement circulated through the global engineering community, the reaction was equal parts admiration and disbelief. Researchers in the United States, Europe, and Japan began quietly pulling the technical documents. Defense contractors took notice. Medical device companies started making calls. Because if Betavolt had really done what they claimed, the implications stretched far beyond a single product. They pointed toward a future where an entire class of devices never needed charging again. And to understand why that matters so deeply, you first need to understand the invisible process powering every single atom inside the BV100. The science of beta decay. Here's where most people's eyes glaze over, but stay with this, because once it clicks, it changes how you see energy forever. Deep inside the BV100, there is no combustion, No chemical reaction eating itself alive the way it does in a lithium battery. No sunlight being captured, no mechanical movement being converted. Instead, there is something quieter, older, and almost incomprehensibly patient happening at the atomic level, a process called beta decay. Every atom in the universe is trying to find stability. Some atoms are already there. Others are what scientists call radioactive. Their nuclei are slightly unstable, and over time, they release energy as they shift toward a more balanced state. Beta decay is one of the ways this happens. During beta decay, a neutron inside the nucleus transforms into a proton, and in doing so, ejects a tiny high-speed particle called a beta particle, which is essentially a fast-moving electron along with a burst of energy. The key word here is slow. Beta decay doesn't happen all at once in a violent explosion. It happens gradually, continuously, over a time scale measured not in minutes or hours, but in years, sometimes decades. The rate at which a radioactive material decays is measured by its half-life, the time it takes for half of its atoms to decay. And the isotope Betavolt chose for the BV100, nickel-63, has a half-life of 100 years. You heard that right, 100 years. That means after 50 years of continuous operation, the BV100 still has roughly half its fuel left, still decaying, still releasing beta particles, still generating energy just at a gradually reduced rate. There is no sudden death, no cliff edge where it stops working. It fades slowly, gracefully, like a candle burning down over a century rather than a match burning out in seconds. But capturing that energy, turning a stream of invisible particles into usable electricity, that's where the real engineering challenge begins. How nickel-63 becomes electricity. Knowing that nickel-63 releases beta particles is one thing. Turning those particles into a current that can actually power a device is something else entirely, and this is where Betavolt's engineering becomes genuinely extraordinary. The process is called Betavoltaics, and the core principle is closer to a solar cell than to a traditional battery. Just like a solar cell converts photons of light into electricity, a Betavoltaic cell converts beta particles into electricity. But the execution is dramatically harder. When a beta particle, that fast-moving electron ejected during decay, strikes a semiconductor material, it knocks loose other electrons inside that material, creating what's called electron-hole pairs. Those displaced electrons create a small but measurable electrical current. Capture enough of them consistently, and you have a power source. The problem is that doing this efficiently at a microscopic scale, without the semiconductor degrading from constant radiation exposure, had stumped engineers for decades. Betavolt's solution was to use diamond as the semiconductor layer, not natural diamond, synthetic diamond, grown in a lab with extreme precision at the atomic level. Diamond is one of the hardest materials on Earth. But what matters here isn't its hardness. It's the fact that diamond has an extraordinarily high resistance to radiation damage. Where traditional semiconductors like silicon would degrade within months or years under constant beta particle bombardment, diamond holds its structure far longer, maintaining conversion efficiency across the kind of timescales the BV100 demands. The BV100 layers ultra-thin sheets of nickel-63 between these diamond semiconductor layers in a precise sandwich structure, source, converter, stacked with almost unimaginable precision at the micron scale. Each layer of nickel-63 is only 2 microns thick. To put that in perspective, a single human hair is roughly 70 microns wide. The radioactive source inside this battery is thinner than 1/35th of a hair. But here's the tension that doesn't go away just because the design is elegant. You are, by definition, building a device that contains radioactive material and is meant to be placed inside human bodies, embedded in military hardware, and launched into space. The question that every engineer, regulator, and skeptic kept asking was simple and terrifying. What happens if it breaks? That answer required a completely different kind of engineering, and it pushed Betavolt into territory that had never been mapped before. The diamond semiconductor layer. The diamond layer inside the BV100 is not just a clever material choice. It is the single most critical reason this battery can exist at all. And understanding why it works reveals just how precisely Betavolt had to engineer at a scale most people never think about. Radiation damages materials. That's not a side effect or a flaw in the design. It's a fundamental physical reality. High-energy particles slamming into a solid material at high speed displace atoms, create defects in the crystal structure, and over time, degrade the material's ability to function. For a device meant to last 50 years while constantly being bombarded from within by beta particles, material degradation isn't just a concern, it's an existential threat to the entire concept. Silicon, the semiconductor that powers virtually every chip, solar cell, and electronic component on the planet, cannot survive this environment. It accumulates too much radiation damage too quickly. Gallium arsenide, another high-performance semiconductor, has better radiation tolerance, but still falls short of what the BV100 demands. Diamond specifically, synthetic diamond grown through chemical vapor deposition, sits in a category of its own. The carbon atoms in diamond are bound together in one of the most tightly packed, structurally rigid arrangements found in any material on Earth. That rigidity makes it extraordinarily resistant to the kind of atomic displacement that radiation causes in other materials. Beta particles pass through, knock a few electrons loose to generate current, and the diamond lattice largely shrugs it off and holds its shape, year after year, decade after decade. But growing diamond at the purity and precision required for semiconductor use is not simple. It is expensive, painstaking, and technically demanding in a way that makes conventional chip manufacturing look straightforward. Betavolt had to develop and refine deposition techniques capable of producing diamond layers at exactly the right thickness, thin enough to allow efficient energy conversion, thick enough to maintain structural integrity, and provide adequate shielding over a 50-year lifespan. Then came the most demanding part of the entire project. It wasn't building one layer. It was building dozens of them, stacked in perfect alternating sequence, each one aligned and bonded, without introducing defects that would compromise the whole structure, all within a device the size of a small coin. The margin for error at every step was essentially zero. And yet, the device works. The electrons flow. The current is stable. The radiation stays contained. But stability inside the lab and stability across 50 years of real-world deployment are two entirely different promises, and the engineering challenges waiting on the other side of that gap were unlike anything Betavolt's team had faced before. The engineering nightmare. Building a battery that lasts 50 years sounds like a goal. Living with the engineering consequences of that goal is something else entirely. When Betavolt's team moved from concept to prototype, they ran headfirst into a wall of problems that don't show up in physics textbooks. Problems that only emerge when theory meets decades of real-world stress. The first was radiation shielding. Beta particles are relatively low energy compared to other forms of radiation, which is part of why nickel-63 was chosen. But relatively low energy doesn't mean harmless, and containing them inside a device small enough to implant in a human body required shielding solutions measured in microns, not millimeters. The diamond layers themselves provide a significant portion of that shielding, but the housing, the bonding materials, and every interface between layers had to be engineered with equal precision. A single gap, a single microfracture developing over decades, could compromise containment. And because this device is designed to outlast most of the products it powers, Betavolt couldn't just test for 5 years and extrapolate. They needed materials with known, documented stability across timescales that pushed the limits of accelerated aging tests. Then came the thermal challenge. Even at microscale, radioactive decay generates heat. Not enough to burn, but enough, over 50 years, to stress the bonding between layers, expand and contract materials through thermal cycling, and gradually introduce the kind of microscopic fatigue that ends devices long before their fuel runs out. Managing that heat without adding bulk or compromising the shielding structure required a level of thermal engineering that hadn't existed in this form before. But the deepest problem wasn't physical. It was this. How do you verify that something will work for 50 years when you've only existed as a company for a fraction of that time? Every claim Betavolt made rested on materials science projections, decay rate calculations, and accelerated stress modeling, not on a battery they'd watched run for half a century. And that gap between projection and proof is exactly where the world's skeptics were sharpening their questions. 50 years of power. Stop for a moment and actually let that number land. 50 years of power. 50 years of continuous, uninterrupted power from a device you never plug in, never recharge, never replace. The last time you held something for 50 years, it probably wasn't electronics. It was a piece of furniture, maybe a photograph. The idea that a power source could outlast multiple generations of the devices it's meant to power isn't just impressive, it fundamentally breaks the assumptions built into how electronics are designed, manufactured, and sold. Every device you use today is built around the assumption of battery death. Smartphones are engineered with 2 to 3 year battery cycles in mind. Medical implants require surgical replacement every 7 to 10 years just to swap the battery. Remote sensors in pipelines, weather stations, and industrial equipment demand maintenance crews, replacement schedules, and logistical infrastructure just to keep the lights on. The cost isn't just financial. It's operational, it's human, and in places like the deep ocean floor or the surface of Mars, it's simply impossible. Stop for a moment and actually let that number land. BV100 doesn't just extend battery life, it removes battery life as a constraint entirely for a whole category of devices. A pacemaker powered by a BV100 could last the patient's lifetime without a single surgery to replace the power source. A sensor buried in a concrete bridge could monitor structural integrity for decades without anyone needing to access it. A satellite in low Earth orbit could operate its onboard systems long after every lithium battery on the same mission has gone dark. But here's the tension that sits underneath all of this promise. The BV100 currently produces just 100 microwatts of power. That's enough for ultra-low power electronics, sensors, medical monitors, communication modules, but nowhere near enough to charge your phone or run a laptop. The energy density per watt is still far below lithium-ion for high-drain applications. This is not, yet, a replacement for the battery in your pocket. The question that determined everything about the BV100's future wasn't whether it worked. It was whether the applications that needed it most could be unlocked before the world lost patience with its limitations. Real-world applications. The moment word spread about the BV100, the calls started coming in from directions Betavolt may not have fully anticipated. Because when you build something that produces stable power for 50 years without maintenance, you don't just attract consumer electronics companies. You attract the people who operate in environments where sending a maintenance crew is either catastrophically expensive or physically impossible. And that list is longer than most people realize. Start with medicine. Cardiac pacemakers, neurostimulators, cochlear implants, drug delivery pumps, the entire category of active implantable medical devices is constrained by one brutal limitation: batteries die. A pacemaker battery lasts roughly 7 to 12 years, after which the patient undergoes surgery not because the device failed, but because the power source did. For elderly or high-risk patients, that surgery carries real danger. A nuclear micro battery with a 50-year lifespan isn't just convenient, it could be the difference between a routine implant and a lifetime of repeat procedures. Then there's the military. Soldiers in the field carry an extraordinary weight. In batteries alone, estimates suggest a combat soldier on a 72-hour mission carries roughly 20 pounds of batteries to power communications, sensors, and night vision equipment. Devices powered by BV100 class batteries would eliminate that weight for low-drain equipment entirely. In remote surveillance, autonomous underwater vehicles, and border monitoring systems, the ability to deploy hardware that runs for decades without resupply isn't an advantage. It's a strategic transformation. Space is where the implications become almost surreal. Solar panels lose efficiency the further you travel from the sun. Chemical batteries degrade in the radiation environment beyond Earth's magnetosphere. Nuclear power has always been the answer for deep space missions, but at the scale of the BV100, you could power onboard instruments, communication relays, and autonomous sensors on missions that current battery technology couldn't sustain for a fraction of the duration. And then, quietly underneath all of these headline applications, sits the one that could touch the most lives: the Internet of Things. Billions of sensors, trackers, environmental monitors, and connected devices are currently limited by how often someone can physically replace their batteries. A world where those devices run for 50 years untouched isn't just more convenient, it's a fundamentally different kind of infrastructure. But none of this happens unless the hardest problem of all gets solved: why the world is watching. When a technology attracts attention from the medical industry, the defense sector, the space industry, and the consumer electronics world simultaneously, that's not hype, that's a signal. And the signal the BV100 sent was loud enough that research teams in the United States, Europe, South Korea, and Japan began accelerating their own Betavoltaic programs almost immediately after Betavolt's announcement. You don't mobilize that kind of international response for a novelty. What the world recognized and what governments were slower to say publicly was that nuclear micro-batteries represent a genuine strategic technology. The country that masters scalable, safe, long-life nuclear energy at the device level doesn't just have a better battery. It has an advantage in every domain, where power supply is a constraint which, when you think about it carefully, is nearly every domain that matters: medical autonomy, military endurance, space exploration, critical infrastructure monitoring. The leverage is enormous. But the race isn't just geopolitical, it's scientific. The BV100 is a proof of concept, not a finished product. Its 100 microwatt output needs to scale. Its manufacturing process needs to become cost competitive. The synthetic diamond layers that make it work need to be producible at volumes that consumer and industrial markets demand. None of that is guaranteed. None of that is easy. And Betavolt knows that the gap between a working prototype and a product on a factory floor has swallowed more promising technologies than anyone wants to count. The tension that defined the BV100's moment in the spotlight wasn't whether the physics worked. The physics worked. The tension was whether the world, its regulators, its manufacturers, its supply chains, could build the infrastructure around a technology this unusual, this unfamiliar, and this consequential fast enough to matter. The battery that changes everything. The battery that changes everything. Here's what it comes down to. You are living at the exact moment when the most fundamental assumption in all of consumer electronics, that every device eventually runs out of power, is being directly challenged for the first time at a commercial scale. Not in a laboratory notebook, not in a theoretical paper. In a working device you could hold between two fingers. That assumption is so deeply embedded in how you live that you've never once stopped to question it. You charge your phone every night. You replace the batteries in your remote. You schedule surgery to swap the power source in a pacemaker. You build maintenance routes into infrastructure just to keep sensors alive. That's the world you've always known. The BV100 is a direct attack on every single part of it. Inside that coin-sized device, nickel-63 atoms are decaying right now, slowly, patiently, unstoppably. Each decay event releases a beta particle that travels microns through a diamond semiconductor layer, knocks electrons loose, and contributes to a current so stable, so consistent, so indifferent to the passage of time that it will be flowing the exact same way in 2074. No lithium degrading, no electrolyte drying out. No charge cycle wearing down the material from the inside, just atomic physics executing the same process it has been executing since the isotope was synthesized on a clock that runs for a century. But here's what makes this moment genuinely historic. The BV100 isn't the destination, it's the proof that the destination exists. Right now, its output sits at 100 microwatts, enough for sensors, implants, and low-power electronics, but not yet enough to power the full range of devices that could transform. The scaling challenge ahead is real, and it is hard. Synthetic diamond manufacturing at commercial volume, regulatory frameworks built around a radioactive source the size of a fingernail, output levels climbing from microwatts toward milliwatts and beyond. None of that happens automatically. But the physics is proven. The concept is no longer theoretical. And once the world has seen that a device this small can generate power for this long, the question stops being whether nuclear microbatteries will change how energy works and becomes only a matter of when.